I'm going to go ahead and get started. So I just want to thank everyone for joining us here today. We're really glad to have you here. Really excited about this webinar and very grateful that we can still gather virtually during these unprecedented times. So we're here today to talk about the considerations of liquid cooling and some of the benefits of switching to a liquid cooling in your designs. But just sit back and relax and enjoy the webinar. In the takeaways, you'll receive a copy of the presentation along with some other tools that you can use and resources to feel empowered about liquid cooling. And that's really the point of being here today, is to let you know that liquid cooling is not scary. So if you look up liquid cooled power supplies, you know, the first thing you're going to see is gamers. And if gamers can do this, you guys can do this too. And we're here to share that with you. Just a little background on Astronaut TDI. We're a power supply and EMI filters company. So we design and manufacture power supplies and EMI filters. We're a privately held company by Tinicum. And the way our company kind of operates is that we're focused on 3 business units. So we split into high power, which we classify as more than 1 kilowatt, low power, which is anything under 1 kilowatt, and then EMI and RF filters. We have over 60 years of experience in the power industry, and 7 out of the 750 employees that we have worldwide, at least 15% or more are engineers or technical professionals. So we take a lot of pride in being a technical company and put a lot of investment in our engineering. So that's kind of empowered us to be leaders in liquid cooling. So just a little introduction of me. I'm Tamana Kamra. I'm your host today. I come from the high power business unit. I'm a marketing engineer. And I get a lot of questions from the field on liquid cooling, a lot of concerns or more just informational questions. What do I need to know? So today I brought in the big guns here today to answer your questions. And so I'm going to introduce our panelists quickly. We have Tunj Aikas, who's the VP of Global Operations for the EMI BU at Astronaut TDI. He has a PhD from Rutgers University and more than 18 years of experience in mechanical engineering. And he's also written 17 peer-reviewed papers and conference papers as well. I also have Matt Furman here. He's the mechanical engineering manager here at Astronaut TDI. He has a bachelor's in mechanical engineering from Binghamton University and 10 years of experience in electronics packaging. And with that, I'm going to jump into my first question for you guys, and that is, why would anyone go liquid cooling? Why make the switch, and what are the benefits?
Thanks, Tamana. Thanks for the introduction. Before I answer that question, I'd like to spend a minute on why we need cooling at all. So despite the advances in technology, all power electronics devices have less than 100% efficiency. So therefore, a certain percentage of that power is lost in heat. And that wasted power increases component temperatures. And if not properly maintained within the operating conditions of the part, it can impact the system reliability. So that's why thermal management of electronics devices plays such a critical role for design and development of power systems. The most widely used method of cooling is air cooling due to its low cost and low complexity. But air cooling does have its limitations. The biggest limitation and the main benefit for selecting liquid cooling is power density. The higher the power density, the more heat generation and the more demanding the application from a cooling standpoint. So what I mean by power density is power density translates to how much power you can fit in a smaller space. For example, you can see here on the slide, we have Tamana supporting the air-cooled cabinet and also as well as the liquid-cooled cabinet. The secret sauce for why liquid cooling is more effective than air cooling is due to the greater heat transfer coefficient, which can be 10 to 100 times higher than that of air cooling. So in the slide here, you can see that you can fit a little, higher power in a smaller form factor with liquid cooling. So that's the key benefit. And Tunj, do you have anything to add?
Yeah, we can talk about the other aspects, other benefits of liquid cooling, primarily on the environmental and system design side. So if you've been to any IT room, where all the servers are cooled by, fan-cooled power supplies or servers, you'll appreciate the noise aspect. Water cooling provides a much quiet environment, especially in the office spaces or other personnel will be working nearby these equipment. Water cooling or liquid cooling also provides a superior weight to power ratio. This is pretty much in line with what Matt described with the power density. Less known benefits of liquid cooling also includes superior temperature control. And what I mean by that is because of the greater heat capacity of liquid compared to air, the temperature gradients within the unit are much smaller. And liquid cooling basically enables users to control the absolute temperature of components in a much precise fashion. Water-cooled systems are usually protected from polluted environments, from ingress protection as well. Also, water-cooled solutions are scalable. We will be discussing, different flow arrangements in the upcoming slides, but you can easily add or remove units once the cooling infrastructure is built. That also enables users to add, power supplies or water-cooled units onto their existing systems. So they do not have to design a brand new system. This basically provides them a platform where they can easily add more power or take out power or add other components that are easily adaptable to their existing water-cooled solutions.
Yeah, I also just want to add that it's with air-cooled power supplies, it's difficult to control where the heat is being ejected. So typically the heat will be ejected into the room, the same room, the location of the power supply, like out the back, the downwind of the fan. Whereas in a water-cooled solution or a liquid-cooled solution, you can choose to exchange the heat in a remote location.
Absolutely.
Yeah. So it sounds like the two big factors here are definitely power density. So you can see on the pictures on the right, you get almost 3 times the power density with liquid cooling in the same amount of space. You can see me trying to climb that the air-cooled cabinet. It's rather big, and the liquid-cooled cabinet, which is smaller, actually delivers more power. And then the second thing, it seems like, is the environment. So you can work in an ultra dirty or ultra clean environment with liquid cooling. So a lot of great benefits here. So my follow-up question to you is, with air cooling, it's pretty straightforward. Air goes from the front of the unit to the back and cools the units. How does heat dissipate in a liquid-cooled power supply?
Let's start with the component level, Tamana. So typically, in a typical application, the heat-generating components, power devices, are mounted on heat sinks or cold plates or heat exchangers. Usually, there's a thermal interface material between them to reduce the contact resistance and provide better conduction path. The wild heat generated with these devices then raises the heat sink temperature, which is illustrated as a green block in our cartoon sketch. As the wall temperature, as the heat sink temperature goes up and water starts flowing through the cooling channels, water picks up the heat from the metal, and then with the proper flow rate, it transports it to a remote location where this wild heat from the components are rejected to whether an outside air through a radiator or to another liquid media by a chiller.
Awesome. Okay.
Myra, so Matt, would you have anything else to add?
Yeah, I think one of the important key factors to removing the heat from these devices is having good thermal contact between the device and the heatsink. That's paramount. That's key. So can't stress that enough.
Okay, very cool. So you guys have me convinced liquid cooling is awesome. the heat dissipates well. So what would you say to customers that maybe want to make the switch to liquid cooling, but aren't really sure what to start? You know, what do you need and what do you need to consider for your system?
So first of all, you know, power supplies can be designed in all different shapes and sizes based on the application or the industry. So some of the key factors that you should consider when designing around liquid cooling would be, you know, the system flow rate required for effective heat exchange to take place, and the capacity of the pump to provide coolant to the power supply in terms of flow rate and pressure head. So the main components of a liquid cooled system are, as you can see here, are the reservoir, which needs to be properly sized to provide enough coolant to the entire flow volume of the system. Any hoses or piping which would deliver coolant to and from the power supply. Fittings which you'd use to make your connections. Fittings are highly customized and they cover a broad spectrum of types, sizes, and features such as valves. Also pictured here is a manifold if you're going to connect more than one unit in the same system in parallel. And then eventually a heat exchanger, which will remove the wasted heat from the coolant. And then there's the pump, which needs to be sized to provide to overcome any pressure drop introduced by the components making up the coolant system. What's known as a chiller is a piece of equipment that contains all of the required components, obviously with the exception of the manifold and the heat load or the power supply itself. Everything I just mentioned, all the coolant hardware, must be compatible with the selected coolant itself.
Okay, yeah, so, you know, in this diagram, it does say example power supply, but that could generally be any of your liquid cooled components, right? You know, or your liquid cooled system. So it could be your laser or your UV curing system or your radar, whatever you're cooling.
Absolutely. I'm sorry to interrupt, Amanda, but yes, you're absolutely correct. And that's, you know, we mentioned one of the benefits of liquid cooling is that, you know, it's scalable, it's adaptable. So as we depicted on the sketch, you know, there's a manifold. So, you know, more heat loads, more power supplies, more components could be easily added to this diagram to customize based on the application needs.
Awesome. Okay, so Matt, you mentioned coolant. So why don't you want to kind of walk through the different kinds of coolants available and you know, the benefits of either or?
Sure. When you're selecting your coolant, there are environmental considerations that need to be taken into account. First of all, the thermal characteristics of the fluid itself and its compatibility with the plumbing materials. As you can see on our chart here, in most applications, distilled or deionized water is the best coolant medium due to its heat carrying capacity, its low cost, and its availability. However, the trade-off is that if you are designing in an application where the environment will drop below 0 degrees C, obviously you don't want to use water there because the water can freeze. So in that application, we would recommend a glycol and water mixture, which can, you know, you can adjust the percentage of glycol to water based on the application. So if you're going down to temperatures of minus 40 degrees C, you would increase the glycol content to 60%. However, with that, the trade-off is if you're using a different glycol doesn't have as good thermal performance. Typically, you'll see higher temperatures in your components with glycol. So that's some of the design consideration you'd have to make there.
So I love the emojis, by the way, guys. I don't know which one of you guys picked, but they're really cute.
Clip art, gotta love it.
Water and glycol water mixtures are the most typical coolants in high performance applications. And then, I couldn't help but realize that, so we included the transformer oil and the floor inerts engineered fluids. I don't know if our audience are familiar with, especially the last one. But both transformer oil and floor inerts are electrically insulating materials. So, they're higher cost, their thermal performance are not great, and they require high complexity. So one could wonder, why would we ever use that? And the answer is they have special applications where, because of the insulating properties, you can submerge the components directly in these fluids. And the benefit of that is, when you bring the coolant in direct contact with the component, your thermal performance, your cooling performance gets enhanced significantly. So there's a trade-off. The liquid themselves are not that great thermally. However, the fact that you can bring them in contact, direct contact with the components, kind of offsets that deficiency. So those are also used in certain niche applications. Transformer oil is widely used in the big transformers, obviously, but in the power supplies as well, especially for outdoor applications.
And just as an example, in terms of the design complexity for the floor inert, the reason we have the 3 of those tool symbols signifies the high complexity to design around, is that when you're selecting, if you were to select the fluid like the floor inert, the floor inert molecule is very, very small, so it's subject to leaking. So you have to take special considerations, and also a coolant such as that will extract elastomers from any gasket seals that you might have in your design. So you have to make sure that the material selection takes this into consideration, because there are gaskets, materials that will be something you can use with a floor inert.
Yep. So I definitely want to get to that material selection in a second, but I did jump ahead of myself here. A question I had that kind of came up in system designing, how do you kind of decide if you have multiple units? So I know we talked about how you can have multiple units and multiple manifolds, but how do you decide what kind of configuration you want to do, whether it's series or parallel? What do you take into account?
Yeah, so this is the fun part, in my opinion, of this problem, is kind of solving a puzzle here. So there are 2 main configurations. One can argue that hybrid is a third option, which is obviously very true. But let's talk about the 2 main ones. So parallel configuration is where there's a main incoming flow. There's a manifold before the units that are being cooled, and the manifold distributes the incoming flow into different branches, and then there is a secondary manifold at the exit that collects all the flow from every branch, and then takes it to the heat exchanger, radiator, whatever the means to reject the heat out of the system. In series, it's not so. You do not have the manifolds. Everything is put in series, one after the other one, basically. So both configurations have pros and cons, and system engineer will have to determine which one suits best for their specific application. I think a key piece of information is that the pressure drop increases exponentially with the flow rate. So from that standpoint, parallel arrangement has a inherent advantage over series configuration, where you split the flow, so you're not pushing as much flow through every single unit. So that ends up lowering the pressure drop. Also, the fact that flow is uniformly distributed, it provides a more uniform temperature distribution across different units. And another significant benefit of parallel configuration is, if something happens to one of the branches, one of the lines, the remaining lines still keep operating. We can flip the table for the series configuration. It's a simpler design. Nobody, you don't need the manifolds or extra fittings. However, you end up, in a typical application, end up with a higher pressure drop. Any failure, any blockage, or any fitting failure in one of the units or in anywhere on the line would impact the entire cooling circuit. So if you have 5 units connected in series, all of a sudden you lose all 5 units. The whole system needs to be shut down. Because you're running the same flow from one unit to the other one, as water picks up heat, the downstream units run hotter than the upstream units. There is some temperature non-uniformity. So in a nutshell, pressure drop, temperature uniformity, and the simplicity or complexity of the design determines which path to choose for its system designer. Or, in most likely cases, there will be a combination of parallel circuits and series circuits in a system.
Okay, yeah, and so I'm assuming since the temperature rises as you go through the units, you're kind of limited to how many units you can put in series as well, whereas in parallel you can put probably as many as you want.
Yeah, I mean, it would be based on the product spec. So if you'd want to pay attention to the inlet temperature, the maximum inlet temperature allowable for the product. But that's correct. Yeah.
Awesome. So yeah, back to what we were talking about in material selection. What are some of the design considerations when you're choosing your material?
Obviously, material selection is a big factor in determining finalizing the design for the system. Specifically for cold plate material selection, so there are three common materials that are widely used in the industry. 2 are more common than the other one, but these are copper, aluminum, and stainless steel. So copper and aluminum are excellent thermal conductors. They have inherent advantages when it comes to removing hot spots or getting superior thermal performance. Copper is more expensive than aluminum, and stainless steel is the most expensive of the 3, and it's the least effective from thermal standpoint. But they all have different applications. They have different applications that they are more suited to. So copper is compatible with almost most of the fluids, but it's not recommended for deionized water applications. There might be folks in the audience that uses deionized water in their current systems, or they're considering designing it. Copper is known to have long-term corrosion issues with deionized water. Bare aluminum has some corrosion issues, known corrosion issues with fresh water or water applications in general. That's the reason we invested a lot of time, resources, and done extensive testing with anodized aluminum. What anodizing does is basically create an electrically insulating, robust layer, thick layer over the base substrate. Because it's electrically insulating, it eliminates the galvanic corrosion due to the similar metals. And that makes it an excellent candidate for deionized water applications as well as glycol water, transformer oil, or it basically makes compatible with pretty much every fluid available. Both copper and aluminum are for moderate pressure applications. Typically, if the line pressure is less than 200 psi, it is not very common, but we've seen applications where the pressure is really high in the line for different reasons. For those high pressure applications, stainless steel. We've seen stainless steel being used more commonly. On the bottom, we show the pictures of our, power supply in two different configurations. We have design experience with copper, with anodized aluminum. Even though it's, rare, we have designed stainless steel heat exchangers, cold plates, and related power supplies as well.
Correct. Just one thing to add, another benefit of choosing aluminum over the other two materials is, aluminum is very easy to machine and extrude. Copper can be extruded, but not in complex, shapes, whereas aluminum can. And stainless steel and copper both have workability issues in terms of machining. You have to really know what you're doing as a machinist if you're going to work with copper and stainless steel, so you're not chewing through your tools. So aluminum is a lot easier to work with.
I also want to add just one last maybe consideration. When it comes to using copper or stainless steel, it adds a lot of weight. So if certain customers, it's preferred to keep the weight down so it becomes a one-man lift. So you can potentially have a lot of metal in any design, whether it's a power supply or a load, and then because of safety reasons, it becomes a two-man lift, which are logistically difficult. Servicing-wise, becomes more difficult.
Yeah,
that's
and you mentioned expandability. So if you're putting multiple systems together in a rack or something, having that extra weight, you have to be able to design around the structural integrity of your cabinet or your rack system.
Very cool. Yeah, so these two obviously love talking about this. They actually co-authored a white paper that goes into more details for what they touched upon today. So we can send that in the takeaways as well. But I want to jump to my last question, which is just in general design considerations to take into account when you're designing this system. We talked a little bit about what you need and what to remember. So what are some challenges to look for and how to mitigate them?
Yeah, I'm sure every engineer has a different opinion on this, but to me, the biggest challenge is identifying the flow rate requirements and the pressure drop. That impacts the configuration. Like I said, I think that's the fun part. You solve the puzzle, you put the pieces together, and then try to optimize the system. So system pressure and the flow rates basically equates to the pump selection. What are the pumps available? How much power do they dissipate? How big they're going to be. Once that is all figured out, all the material used in the system needs to be compatible with the environment. That's one of the biggest design challenges as well, and also packaging limitations. So on one of the early slides, we talked about putting 300 up to 500 kilowatts of power in a cabinetized solution. When you put that much power in a tight space, all the manifolding, all the electrical connections, and they all take up precious space. And how to fit all these components necessary for the design into the limited space is also a very difficult, very challenging, I shouldn't say difficult, fun, but challenging design exercise as well. Matt is our subject matter expert on the sensoring, so I'll let Matt, you
sure
about the detections.
Yeah, so when considering liquid cooling, if you have a liquid cooled system, and you're concerned about, what can go wrong, there are a lot of sensing techniques that you can use to kind of navigate around some of the issues that may arise, such as, temperature sensors. So if you're concerned that you have a blockage somewhere, you can place thermocouples along your manifold or along some of your fittings. and monitor the temperature coming in or going out of your heat load. You can also include a flow sensor to make sure that you're getting the right distribution to your power supply. Also, in terms of leak detection, you can monitor the coolant level in your reservoir to make sure that you don't have any undetectable leaks in your system, and also a humidity sensor. So I want to explain the purpose of the humidity sensor a little bit. So one of the design challenges that we've come across is condensation. And condensation occurs when your coolant temperature is running below the dew point in an uncontrolled climate environment. Now, the dew point is a function of the relative humidity and your ambient temperature. And condensation can build on your surfaces of your cold plate, and over time, that condensation can cause damage to electronics if not properly mitigated. So one of the solutions that we've come up with involves humisealing our PCBs. Humiseal creates a protective varnish layer on the components, and also, modern chiller systems. Another way to mitigate condensation is modern chiller systems that provide the coolant. They can be temperature controlled to adjust as your dew point changes. So that as the temperature drops throughout the day, if it's an outdoor environment, the chiller can adjust its temperature to stay above that dew point so condensation doesn't form.
I think we can't emphasize enough the design consideration on the condensation in a water-cooled system. So oftentimes, we come across with applications where the cabinet needs to be sitting on an outside environment, and the coolant temperature is not controlled. And then we bring up with every customer that there's a concern if the temperature drops below the dew point in a high humidity environment. The system needs to be protected, and I think that's oftentimes overlooked, and it's a second thought. So we really want to bring that up as one of the really hidden design challenges.
There's also always the brute force method of protecting your power supply from humidity by making it completely sealed from the environment, so you don't allow any moisture to even enter the power supply. So to prevent condensation.
Yeah, I mean, so protecting the power supply is obviously very critical to us, but also in a systemized design, there could be control panels, there could be other electrical panels that could be sitting below the plumbing. As the hoses start getting chilled water and promotes condensation, they could pose an electrical hazard for customers' control circuitry or telemetry or other equipment as well. It's not just limited to power supply.
Yep.
Awesome. So yeah, a lot of great information here today. So I want to thank you guys. But I know it was a lot of information, but I'm here to tell you, we're all here to tell you that liquid cooling, it's not hard. I told you before, if gamers can do it, you can do it, and that we're here to help. So if you're ready to make the switch to liquid cooling, you got questions about system design, system level design for liquid cooling, you can actually contact one of our FAs here. We're here to help. So I'm going to wrap that up. And with that, I'm going to open the floor to any questions from the audience. So if you have a question, you can actually just put it in this chat box and we will answer them. All right, so someone asked, as far as heat sensor, would you look at thermistors or RTDs?
I'll take that question, Matt, if you don't mind. So but both could be used. It all depends on the level of accuracy that's required. So typically thermistors will be just fine. If really the temperature needs to be controlled in a more precise fashion, then RTDs provide more accuracy. But
yeah, our experience is that thermistors need to be calibrated before they can be used.
sure. But it's a little less expensive and a kind of more a basic approach.